Hi everybody. This is a discussion for the Computational Physics Lab 3 where we will mostly do Fourier Transform. Now while in the lecture we discussed about discrete Fourier Transform, Nyquist sampling theorems, aliasing, etc. So we saw that in the discretized version the Fourier Transform can be written in the following way. Now let us count how many mathematical operations we need to do to calculate the Fourier transform. So we want to calculate the Fourier transform. So we want to calculate all ALs, and there are n of them. Each calculation, as this formula suggests, requires a summation over n. So n calculations, essentially n calculation of this quantity inside the summation. So which means in one dimension Fourier transform, or let's say DFT, of size n, the number of operation involved is n square. Right. Now the question is that can this be the number of operations can be reduced, because otherwise if n gets large, n square is a very n square will very fast get a humongous number. And if it is like three dimensions where you have n into n into n cube, so it will be n to the 6 operations, which is really large. It will take a lot of time to calculate. Now a way forward was suggested by originally Gauss in 1805 and then rediscovered by Danielson and Lanzos. So they showed that if there is an n-length Fourier transform, it can be broken into two Fourier transforms, one with the odd and the other with the even components. Like we are summing over n here, small n here, so n equals to 0, 2, 4. So that will become one Fourier transform, one DFT, and the 1, 3, 5 will become another DFT. And it's obvious that I will get n by 2 here and n by 2 here. So what is the advantage if I can do this? Well, we immediately see that initially I have a n transform, and this will require n square operations. Now I have broken it into n by 2 and n by 2 transforms. Each n by 2 Fourier transforms will require n by 2 square operations, and I have two of them, so this is the total, which is n square over 4 plus n square over 4. So immediately see that I need half of the operations here. But they also showed that this can be then further divided into another n by 2, n by 2. So each of these will have now n by 4 and n by 4. And this can be done further and further. So now if I just see here, so if I have n by 4 here, so now we know that how to calculate. So this times 4, which will finally give me n square by 4 operations only. So I can not do n square operations, but I can do smaller and smaller number of operations. And you develop an algorithm, and it's not a very simple algorithm, it's quite complicated an algorithm. That's why we don't discuss it in a 3 lecture Fourier transform course here. But this is what you will be using, because these algorithms are implemented in all Fourier transform packages. In Python there are multiple implementations, so we'll be using this algorithm. That's why I thought that I will discuss it with you. So this algorithm is called fast Fourier transform. And then this is the basic of the algorithm that I discussed, but this is, as I said again, it's quite complicated and there are a lot of things in here which we will not discuss. This showed that what required n square operation would now require n log to the base 10 n operations only. So which means that that's why it's called a fast Fourier transform. So this is the only small introduction to first Fourier transform that I wanted to tell you. And now what we will do is that we will look at some examples of Fourier transform in the Colab. And I request you to go through this example, try it yourself by typing them in your Colab, and then come to the class such that you can get more time to do the problems in the class which are designed for the class. All right. So let me first demonstrate to you how to use SciPy. There is a package called Scientific Python or SciPy, and that has an FFT library called FFT Pack. So how to use SciPy FFT Pack? Let me just show you that first. Examples of this, obviously, I will show as we'll see as we go along. But to call this library, so let me just write import numpy as mp, because that is something that anyway we will need. And we also will like to plot things. So this we have seen already. Now there is the additional thing, which is import scipy.ffmpeg. So this is a library or module, and then that module has a submodule called ffmpeg. Scipy is a greater module, and that I will just import as FFT. Okay, so there is FFT in NumPy as well, but we will be using SciPy just to learn something new. And then once we go through the examples, you will see that how this FFT is implemented, or how you do one-dimensional and two-dimensional FFTs with this. All right, now so let's see a very simple example where we will do the Fourier transform of uh, uh, of a sine wave, a function that is given by a sine wave. So this is the example for you. It's very simple. So it says that consider a function ft, which is just the amplitude one, a sine wave 2 pi t by capital T. Show that the better the Nyquist sampling, we recover the frequency of this time series. For better than Nyquist sampling, we recover the frequency of this time series. Okay, so first what we will do is we will just plot this function, which I know that you already know. So we'll just go through this quickly. So I decide on this, and then I have to, so there is capital T is definitely the time period, which I choose to be 1. Remember that in one of the classes, I think the first class itself, we said that we have to choose an unit for our things, or for whatever we represent, or we make things dimensionless. Here, by choosing the time period to be 1, I'm making things dimensionless. If the time period was 13, So you will measure everything in the units of the time period. Now it's a sine wave, so one time period will give you one oscillation. So I choose, say I choose to see 20 oscillations of this sine wave. So T max is taken as 20. So what now I will do is that I will create uh, a set of time sample points. This is just to see the plot, so this is much better than Nyquist sampling. This is to see the sine wave essentially. So this I say that np dot lin space. So what lin space does is if we give it two numbers like 0 and t max, it will create n points between 0 and 2 t max, and that n I have given here. Okay, and then correspondingly I will calculate the y, and the y is nothing but just I calculate from its definition, which is 2 star np dot pi is the pi, and then times t, and the t I have given the name tc, and divided by capital T, which is the sine wave. And now I want to plot it. So to plot, remember that so this is what I use always, which is to clear if there is any other plot before. This is not really required if you are doing it in PyLab, in a Py book like this, but when you will run your Python scripts on something, then probably will need all this. And okay, so what do I do? So I first level the x-axis. The x-axis definitely is time here. I use a font size of say 14, and I use the y-axis. Y-axis, let's call this f as a function of t. You can use r over here and then this within dollar sign. So what this is called is rich text, latex fonts. So this just looks like the fonts that one uses for mathematical symbols. I will not go into much further details on this. So this is x and y that one I have given, and then I choose the limit of the x-axis to be 0 to t max, and limit of the y-axis, uh, it obviously goes from -1 to +1. I just choose a little bit of extra such that I can see it properly. And then finally I plot. I plot what? I plot TC versus YC. I use this, which is to show, say that join all the points by a line. I use a color blue to plot. You see, I can specify all of these. I can also specify the width of the line, which is by default 1, but still I call it, tell it that use a line width of 1. So this will plot now the sine wave. So let's see that. It's connecting to the server right now. Now this is just demonstration. Obviously, I have to discretize the function to plot it, but I have used a very high number of discretizations as that it just looks like a sine wave, which you see that it looks like a sine wave, quite nice one. Now, let us calculate the Nyquist frequency or Nyquist interval to plot this. So what is the frequency of the sine wave? Frequency of the sine wave is just 1 by the t, which is obviously 1. And because the frequency is 1, what is the Nyquist rate? dt Nyquist is 1 by 2 by frequency. The maximum frequency, it has only one frequency. So this is essentially the Nyquist rate, right? So let's just run it once, so you know that you can calculate it by I only, but just to see there's the frequency is this, and if I want to also see what is the dt Nyquist, then it is 0.5. So what now I do is that I say I choose a dt which is better than the Nyquist rate, which means it should be smaller than zero point 0.5. So let us choose it like zero point 0.1, which is definitely smaller than zero point 0.5. So if I choose dt to be zero point 0.1, I can now calculate how many points do I need. So every zero point 0.1 time interval, I am sampling the first function, and I can ask the question that how many times I have to sample the function. So n sample is essentially p max by dt, but also I want this to be an integer, and I want this the p max by dt can be like say 100.3. So I want to sample it to a 100.4, which is higher than 100.3. So if this is a fraction, I can choose the next integer by saying that np dot ceil. So ceil is nothing but it's essentially ceiling. So if you think of you are in a room, so you get a point which is in between the floor and the roof or the ceiling of the room. So the floor is say 2 and the ceiling is say 3, you get a point 2.1. So if I say np dot ceil, it will 2.1 will go to the ceiling, which is 3. And if I say np dot floor, it will go to the floor, which is 2. Okay. And then I convert it to integer. So this is my number of samples that I've chosen with that dt. So the t that I will use, so that is the sampling t. So let's say t sample. So those are np dot line space 0 to t max, but now nc. Instead of nc, I have n sample. And I can calculate the corresponding y samples, which is again the same thing as it is here. So I'll just copy and paste it here and change tc to t sample. And let us just again plot this and see how this looks like, how we have sampled it. So I say plt dot plot t sample y sample. But now instead of point, I mean, I don't want to confuse between what I have plotted earlier. So I just point it with a small zero, which will plot big points on that. And I choose a color, maybe black, and that's it. So that is what I will plot and see how it looks like. Now it says that there is some problem. The problem is that I have done a spelling mistake here. Okay, what you see are this series of points. These points are the points where the function is sampled. Okay. The reason you see a kind of pattern here is because of the regular sampling of the function, but that pattern has nothing to do with the function itself. It has to do with the sampling. And this is, you can see in between here and there. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9 samples in between one time period, which is much larger than the Nyquist sampling rate. All right. So till now we have not done any Fourier transform, and now we will do the Fourier transform. And what that we need to do for doing the Fourier transform? Well, so I had the function fx, or what we have called ys. Let's calculate f nu. How to calculate f nu? So remember that the FFT pack, we have given a nickname FFT. So what all I have to do is I have to do FFT. So I have to, from the nickname FFT, I have to call the function FFT. And that function, I have to give the argument, which is the function that I want to do Fourier transform. So ys is what I do want to Fourier transform. So I give that in my argument. But remember that we discussed that we need to give a shift, because the way the discrete Fourier transform is defined, the center of the numbers is nu max by 2 and minus nu max by 2, and you want to think we want things to be symmetric about the center. So you have to do a shift, and then for that also there is a function called FFT shift. So if I do just this, then I will get the Fourier transform done. But not quite so, because remember that I have that normalization of 1 by root n, which is not included in the Fourier transform routine. So I have to do a np dot square root of n sample. So that completes. So that's all that I need to do to Fourier transform this data. Okay. And then remember that this will have between minus nu max to plus nu max. So we can define the corresponding news, and the corresponding news I can just use the np dot lin space. And nu max in this case is nothing but what we calculate at frequency as frequency over there. Sorry, what we calculated as Nyquist. Uh, yeah. So it's this frequency divided by 2 essentially is the nu max, if you remember the formula for nu max. So let us write here nu max is 1 by dt, 1 by 2 by bt essentially. So that I have to calculate after I calculate dt certainly. So let us do it here. So this you can refer to your notes. You will see that this is the formula for nu max. So we do for minus nu max to nu max, and I have n samples. So this is how the Fourier transform is now calculated between mu and f nu. So we want to plot it. Now we want to see both of these together, and there is a way of doing that by using what we call is this subplots. So like you have those plots where you have one plot and then more than one plot within a given plot. So that's what we will do here. This PLT dot subplot is, if I write 2 on 1, it will have 2 rows and 1 column, and that's what we want here. So I say 2 on 1. So this is the first plot. If I just show you quickly, you will see that how it has appeared. Let me just check what mistake I have made again. I made the same mistake. That's interesting. And this is called ensample. Yeah. So you see that it has kind of shrunken down, and there will be another column, another row here. So once I plt dot subplot. Now in the same configuration, which is 2 1, 2 rows 1 column, I will add the second plot. So I call 2 1 2 here, and let me just copy all these things so that it becomes easier for me to change and plot. So instead of t, my level will be new, and then if I write slash new, it will plot the Roman letter new, and this is slash, say let's call this capital F new, and I will plot from 0 to nu max, because minus nu max is not quite well, and this y limit I will not put, because I don't know exactly what y limit it will have. So this is, I'm plotting now new versus f new. That's it. So let's try to see how this plot comes about. So what do we see? So we see this is supposed to be a delta function, if you remember. It's not quite a delta function. There is a rise and then there is a small fall, and then it continues to be kind of 0. The rise is at the right place. It is at nu equals to 1. And remember, the frequency for us is essentially 1. The frequency is 1 by t is 1, so the frequency is 1. So it gives it at the right frequency. There is a little funny shape other than a perfect delta function, and I leave it for you to think about why that funny shape is there, why it is not looking like a nice delta function, but this kind of funny shape. What you can see is that if I approximate this as a delta function, I will definitely see that the frequency at which the frequency content of the signal is at the frequency equals to 1. So that we see clearly here. All right. So that was the first thing that I wanted to demonstrate to you. And now what we will do is we will almost do the same thing, but instead of a single function, now I will have single frequencies. Now I will have two frequencies. So let me just copy this entirely. So in this problem, the second example, what we will do is we'll consider a function. So let me just write the uh, problem here. Problem is the following, that it says that consider a function. Now we have two sine waves with two different time periods, and it's sampled at an interval dt, which is sufficient for the frequency of t1. So for this it is good, but not for t2. So why we are doing this? Because we want to see the aliasing effect that we discussed in the last lecture. All right. So let's see how to modify. All right. So let's see how to modify the code. So it's not very difficult, obviously. So what we do is that instead of 1, I now define 2t. And let's say this define this as 0.1. So why I defined 0.1? Because if it is 0.1, that will corresponds to the that will corresponds to an Nyquist frequency which is higher than what is for 1, right? So let's say the Nyquist, the frequencies are, there are two frequencies now. So frequency 1 is this by t1, and frequency 2 is 1 by t2. So the Nyquist frequency will be from the will be obviously from the highest frequency. So I can do that by saying np dot max of frequency 1 and frequency 2. So that the highest one will give you the Nyquist frequency. All right. So what will we do? So let's see. Let's ask the question: what is the Nyquist frequency? Here, the Nyquist frequency will be 1 by 2 into highest frequency is 10. So 1 by 20. Nyquist frequency is 1 by 20. So dt Nyquist is 1 by 20. What if we choose dt equals to 1 by 10, which is 0.1? Well, if I choose dt equals to 1 by 10, obviously the t1, which is 1, will work, which we have already seen, but it is much larger. It's twice the Nyquist sampling rate, so it will not work for the uh, it will not work for the second frequency or second time period t2. All right. So we'll see the time period obviously. So let me just do this. And so Tmax is supposed to be written as 20 times T1. And so this is T1 here and T2 here. And similarly here as well, I add the other one, T1 and T2. Remember that TC and YC is just to see the function properly, and TS and YS are the actual samples that we are talking about. Now this remains as it is. This also remains as it is. There is no change because I have just changed the function. And then the plot will also remain as it is. So I don't need much change here, you see, in the code. I guess that it will require to have a tuple inside. So I need two brackets here. That's what it is complaining about most likely. So let me just see what happens if I run this. So there is some problem here. So let's see what is the problem. The problem is that so this should be TC and this should be TS, right? Because so the reason it gave an error is because this has a length of n sample, whatever the n sample may be, and this has a length of, if I write TC over here, this will have a length of NC, which is much larger. So you cannot add two vectors of different lengths. All right, so let's try again. Yeah, you can see now that there are these small oscillations and then there is this bigger oscillation. Okay. So what you see is what you are supposed to get a, a peak at 1 and a peak at 10. We get the peak at 1 all right, but the peak at 10, obviously 10 is not there, but there is a secondary peak over here. And this is the aliasing effect. So that secondary peak, remember, it's going around in the circle in the periodic the frequency axis is periodic for the DFT, so it's going around the circle and sneaking in from here. What if we would have tried better than Nyquist sampling frequency? So instead of 0.1, let us try at 0.025. Why I tried 0.25 is because Nyquist frequency is 0.05, so 0.25 is much smaller than that. So this should give me the two peaks properly, one at 1 and the other at 10. And that is what you see, though the x-axis is not clearly visible here, but you can imagine this peak is coming at 1, the other peak is now coming at 10. So that is quite visible right now. Again, I leave it to you to think about why this peak is smaller and why this peak is larger. And there is a definite reason for that. All right. Given that we have now learned how to do Fourier transform, we will now try to solve a physics problem. So this is the example 3 for you. And for the example 3, I have kept a physics problem, and this is some of you have actually seen the result of solving this physics problem in your general physics lab, because this is how we generated the data for you. The problem is to find the diffraction pattern of a single slit. As simple as that. Now, how do I do that? How do I go about finding the diffraction pattern of a single slit? So for the single slit diffraction pattern, for the single slit diffraction pattern, what the background physics knowledge that you need to have is the fact that the diffraction pattern of a single slit is the Fourier transform, square of the Fourier transform of the slit function. Okay, so let us just start writing the code, and then when it comes to the slit function, I'll show you what it is. So what we will start with is that we'll discretize the slit function is nothing but a function which is 0 everywhere where there is no slit and 1 where there is the slit. Okay. So it looks like 0, then goes to 1, a box, and then goes to 0 again. It remains 1 as long as the slit width. Now to do this, what we do is that we discretize our box, and we choose a discretization of 120 numbers. You can choose a little bit bigger as well. So let's say 1024 numbers. And the length we calculate in units of slit width. So slit width I have chosen to be 1. If you have the slit width given as 0.1, you can divide all your length scales by 0.1 and then it will be 1. And what we do is we keep the slit width at the center of the box and go from minus L max to plus L max. So I choose the L max to be 10 times the slit width. This is just I mean, just to convenience, you can choose 100 times and see what happens. So that's on you. So you should try those exercises. So now what will be the sampling interval? So the sampling interval, I can do the exact same thing as I was doing there. So it is in integer np dot ceil sampling. Sorry. We are calculating the sampling interval, which is L max. L max goes from minus L max to plus L max. The L goes, so it's 2 times L max by DL. I'm sorry, by N data. DL is what we are calculating. And now the slit is also discretized. So I can only make it fall to 0 at a regular interval. So the slit width in numbers, so let's calculate that. So that will be an integer. And again, I will do the same thing. So np dot ceil, or maybe this time we will do np dot round, which will round it off to the nearest integer. And np dot round. So so the slit width in units is this, and then each unit in the discretization unit is dl. So this is my np. This is the number in the slit width. Slit width in number. Okay. So what will I now do is that I will just define a series of zeros, and that can be done as this way. Because remember that the function is 0 everywhere apart from the center part where the slit is 1. So the function is 1 where the slit is and the function is 1. So I define np dot 0. So this is obviously n data number of zeros, so the number of discretization points. But everywhere it is, so now it is defined as 0 everywhere, but everywhere it is not 0. It is non-zero at the middle, and it is non-zero for a width of nw. So if now I can call those indices of the array y. Those indices are, remember that it should start from the center, so which is n data by 2. Go to half of the slit in the left side, so which is nw by 2, and start from there and go to half of the slits in the right side. So n data by 2 is the center again, and half of the slits in the right side. So this half and half in both sides will make it 1 slit width. This we want to keep as 1, because that is the slit on. Now, how is the diffraction pattern defined? Well, I want to plot the slit, so let me just call this, just define this, just like, and I typed slowly now, still I did a mistake, which I can have spotted, and minus L max to L max and N data. So this is my X. Pattern, before we look at the pattern, let me plot the slit first, and I will just borrow the plotting part of the code from the previous thing. Let's see. So here it is X, and this function I call fx, and I don't need this anyway. Just plotting this function, I can make the line width to be 2 here, and the other function doesn't exist, so you know that for block comments I can use these. It will just comment those lines. And here I can the y limit can be minus 0.1 to 1.1, then it will have a little bit of limits in the either side. Yeah, so this is supposed to be minus L max to plus L max. Let's see. the definition of our slit. So now you see that it's a function which is zero everywhere, and then there's a slit. And I want a sin square as the output, which you know is the single slit diffraction pattern. Let's call this pattern as PP. And I do the exact same thing that I did before. So that's the good thing about this. I'm just using the same FFT algorithm for different things. That's it. But now remember that the pattern is actually absolute square of this. So I have to calculate the absolute, which I do by. So this is a complex number. I calculate the absolute and then I square it. So absolute square is the pattern. So that's what I have done. And just like before, I can calculate my, instead of mu, I can calculate my k here, which is the exact same thing what I did earlier, 1 by 2 by PL. And then define, this is K max, define the Ks, which are the frequencies, special frequencies in this case. The special frequencies can be negative. This is K, this I intensity. I think that should be it. Yeah, you can see this nice single slit diffraction pattern. To see it a little better, what I should do is, instead of plotting minus k max to k max, I can zoom in a little bit, and to do that, I can just divide the k max interval, so which will let me see more clearly in the k, and you can see now this nice patterns coming in. So here, a 2D square slit I can define in the following way. First, I need some dimension. So let's say n data is 1024. So I will have a two-dimensional array which is n data by n data, and then I will have a slit which has a certain width. So let me just copy these parts from here. So this will be exactly the same. So I have a slit width of 1. My L max is minus 10 to plus 10 times the slit width. L goes from minus 10 to plus 10, the slit width, and there is a TL, and then there is the width of the slit. All these are fine. So now, if I define the slit, so let me call it slit only. So this will be np dot zeros, but now it's a two-dimensional, so I have a tuple is n data by n data. And now I have to choose the central region of the slit to be 1, and that central region I can choose exactly the same way I have done before. Only thing is that it will be in two dimensions. So let me just copy it again from here. See what is it is doing is, so this is choosing for one of the dimensions, and then I have to choose for the other dimension as well. And the choice is exactly same because it's a square slit. Uh, you need a certain range to certain range in x and y to be 1. Okay. Now the difference comes when you try to plot this slit, because you cannot now plot anymore with the conventional way. of, because it's a two-dimensional thing. So let me just copy a little bit of it and then plot it for you. Okay. So you can use several things. What I will show here is called imshow. So here if I say slit, and it will plot a density of the slit. Density means it will have different colors. Different colors will show different values of this function. So if I show is after this, if I show color bar, so that will tell you that which color shows what value. So let's see once and then it will be clear. So you see what it has done is it has plotted the zeros with this color and the ones with this color. So that's why there is a slit in between, which is 1. Everywhere else it is 0. And if I want to do the Fourier transform of this, just like before, I can do it. So I can just calculate the pattern. I can just use this. And the only difference now will be the fact that instead of a one-dimensional FFT, I'm doing a 2D FFT, so I have to mention it here. So I say FFT2. And obviously this is slit. And for a 2D FFT, I will need to have np dot square root of n data into n data, because I have now n data square data. So obviously square and square root can be taken away. So this goes away. And now again I will use the same idea of color bar to plot what it looks like, the pattern looks like in the Fourier plane, or the Fourier transform, how it looks like. And then you see that it looks like this. Okay. So again, let me do two things here. So one is that it's better if I can see them side by side. So I just change this to 1, 2. So now there is 1 row, 2 columns. And the other thing is that I can also zoom in here a little bit. So instead of plotting all of this, or I'll leave it to you to figure out how to zoom in this. Okay. But definitely, the pattern is, there is a Fourier pattern of the slit. If I make the slit even smaller, or then this will be better visible. To see that you have this pattern, the slit is almost not visible because this, we have gone through very large distance from the slit, so it is like only few points here. But now the pattern is visible. So that's showing you the inverse relationship between the size of the slit and the size of the pattern, or the inverse relationship or inverse support in a plane and in its Fourier plane. So I'll stop here. And what I will request you to do is to go through the video, write the lines by your hand in your Colab and practice, and then come. I'm only giving you the video, not the collab, because if you copy paste or just look at it, you never learn. Thank you.